We will now look at some applications of these integrals. So we start with the mass of a one-dimensional object. So if we consider a bar or wire that's represented by a line segment on an interval from x equal to a to b, and we're going to suppose this bar has a density function given by rho, then the mass of the object is given by the integral from a to b of rho of x dx. So let's consider a thin 4-meter bar. So this will be represented by the interval from 0 to 4. We'll suppose it's made of an alloy whose density is given by x squared minus 3. So let's find the mass. So this is the integral from 0 to 4 of the density function, x squared minus 3 dx. So when I integrate this, I get 1/3 x cubed minus 3x between 0 and 4. So 1/3 4 cubed minus 3 times 4 minus 1/3 0 cubed minus 3 times 0. So we have 64/3 minus 12. And this gives us a mass of 28/3 kilograms. Another application will be work. So the work done by a variable force F when an object moves along a line from x equal to a to x equal to b in the direction of the force is given by the integral from a to b of f of x dx. So if we integrate the force, we can determine the work. One application of force and work that we can easily visualize is the stretching and compression of a spring. So we consider an object attached to a spring on a frictionless horizontal surface. And then the object will move back and forth under the influence of the spring. We say it's at equilibrium when it's neither compressed nor stretched, and this will happen when x is 0. Hooke's law tells us that the force required to keep the spring in the compressed or stretched position x, units from equilibrium, is f of x equal to kx. And k is just a positive spring constant that determines the stiffness of the spring. So when we stretch a spring, then x is greater than 0, so our force will also be positive. To compress the spring, we have x less than 0, so we have a negative force. So let's consider a spring that requires 15 newtons force to stretch the spring 1 meter from its equilibrium position and hold it in that position. So assuming it obeys Hooke's law, let's find our spring constant. So Hooke's law says that f of x is equal to kx. So I know that we have a force of 15 whenever x is 0.1. So I have 15 is equal to 0.1 k. So this gives me 150 equal to k. So that's our spring constant. This means our force is given in general by 150 x. Let's determine how much work is needed to compress the spring 0.5 meters from its equilibrium position. So since we're compressing the spring, we'll have 0 to minus 0.5, and our force was given by 150x. So this is 75 x squared going between 0 and minus 0.5. So 75 times minus 0.5 squared minus 75 times 0, which gives us 18.75. Now let's consider this spring and how much work is needed to stretch it 0.25 meters from its equilibrium position. So we start at 0, and this time since we're stretching, we'll end at positive 0.25. And this will go our force, which was 150x dx. When we integrate this, we have 75x squared going between 0 and 0.25. So I have 75 times 0.25 squared minus 75 times 0, which gives us 4.6875. Let's now determine how much additional work is required to stretch the spring 0.25 meters if it's already been stretched 0.1 meters. So instead of starting at equilibrium, we're going to start at 0.1. Then we're going to stretch it an additional 0.25, so we'll end at 0.35 meters. And our force was 150x. When we integrate, we have 75x squared going between 0.1 and 0.35. So I have 75 times 0.35 squared minus 75 times 0.1 squared, which gives us 8.4375.